So what have we done so far? We've looked at this expression and we've drawn a truth table for it. We've drawn out the logic gates, and now we're going to simplify it. So we're going to use the same tools we've looked at. Let's start with the order of operations. Start with brackets, then look at NOT gates, AND gates, XOR gates, and finally the OR gates. So I'm going to look inside the brackets first. Negation comes before OR, so I'm going to make sure I negate B, and then I'm going to run that through an OR gate with A. All of that is then multiplied by B, which means they're both run through an AND gate. And then the entire mess on the right-hand side here is run through an OR gate with A. So I'm not that interested in what those gates look like at the moment, but appreciating the order of operations is going to help me here. So I'm going to first add in some extra brackets so that I no longer have to think about the order of operations. So I'll just tuck the second half into the expression into brackets as well. Doesn't hurt to over bracket. Okay, let's start simplifying. Have a look at your rule sheet. Does anything stand out? What could we do here? Well, probably from regular algebra, you recognize distributive property. And in fact, if you look at rule 8a, it's that. A and B or C is equal to A and B or A and C. Do you recognize that here? I can use distributive property to take B and multiply it by A, and then take B and multiply it by not B. And that turns out to be interesting because B and not B, we talked about that on a previous slide. What rule does that look like? Well, we know that one as well. A and not A is rule 12a. So this A and not A is equal to 0. Okay, so we're dealing with B's here, but it's the same. It says an input and its negation are equal to 0. So far we have A or BA or 0. And we can go further and say that, well, anytime, and this is rule 9b, that I have an input of any sort and I run it through an OR gate with 0, it's this input, whatever the value of A is, that defines the output. So we can essentially just drop this plus 0. And we know that from regular algebra. We wouldn't write that. So we're almost done. And 9b, we almost didn't have to write out. That one is so intuitive that we're pretty comfortable skipping that one. 15b is the last rule that I recognize. And in fact, the way the rule is written is exactly the way it's written in our equation. It says A or B in A is actually just equal to A. So you can guarantee that that's as simplified as that will get as we're down to a variable. We'll look at the truth table for this in the next slide and see if we're correct. All right, so we want to verify that what we see in the column for A is the same as this whole mess. So hopefully you remember how to create truth tables for Boolean expressions. We want to create the Boolean expression for this left-hand side. Let's start with the inputs. So 2 zeros, 2 ones, and then split those in half. What you may also notice is that you're counting in binary as you move from top to bottom. Well, the first thing working from the inside out that we discovered we need to do, looking at the order of operations on the previous slide, was that we had to find B naught. So we just take the negation of B, that flips all of our inputs. And now we'll look at A or not B. So of course for these ones, we're only interested in columns A and not B. This is an OR gate, so as long as at least one of them is a 1, the output will be a 1. All right, the next step is to take B and what we just discovered for A or not B. So we have slightly different columns that we're interested here. We want this previous one and that guy, B. We'll take the highlighting off the ones that we're not interested in at the moment. So an AND gate is only going to have an output of 1 if both inputs are 1. And finally, now we can look at A or everything that we just looked at in the previous column, B and A or not B. So I'll highlight the columns again that we're interested in here. We want to look at A and that previous one. Okay, so it's an OR gate, so if at least one of those is a 1, then the output will be 1, and if both are zeros, they will be 0. So it looks like that. Now I want you to look at the entire column. Right? We discovered that this entire expression on the far right-hand side is equal to A. What that means is when we look at the inputs in our truth table, they should be identical, and they are. So that shows that our simplification is done correctly. All right, now it's your turn. Try these 3 for practice. We'll look at the solutions together on the next couple slides, but try them ahead of time. It's difficult at first and then gets easier the more practice you have. Okay, let's see if we can squeeze these into 3 slides. Let's look at this first one. So once again, I notice that if I play around with this using 7b, which is the commutative property, I'll write them down here. So 7b is A or B and C is equal to A or B or B and or C. And that's exactly what we have going here. We can essentially shift these brackets over. Why do I think that's a good idea? Well, I noticed that I could actually tuck B or not B into the same brackets. And if I look at my formula sheet, I've got a rule for that. If I have the input A or not A, that's just equal to 1. So using rule 12b, I can rewrite this as A and 1. And this one, almost trivial, but this one, more than multiplication or addition to 0, is one we should look at. And rule 10b tells us that if an input, and we run it through an OR gate with 1, the output will be 1. Because for an OR gate, only one of my inputs has to be 1, so it's irrelevant what A is. And so the output is just A. Sorry, the output is just 1. Got a little carried away there. A or 1 is just 1. Let's try the next one. For this one, I see quite quickly that that looks like something that's redundant. Let's see if there's a rule that applies to it. So it turns out rule 11a tells us that A times A, or A and A, is equal to A. So I can simplify that quite quickly. And maybe you're simplifying 2 at the same time, because I'm also noticing that I've got a B in the second and the third term. Remember distributive property? We usually write it, we think of as forwards, but let's look at what the output of that is, AB or AC. Well, they both have an A, which means we can pull that A out in front and have only the B and the C left inside the brackets. So applying rule 8a, so this was 11a and now we're applying 8a, gives us A plus B, and then left inside the brackets is the C and the not C. Why do I want those together? For the same reason it was helpful over here. So that's rule 12b. C and not C, B and not B, A and not A, that's just equal to 1. And 1 multiplied by anything is just equal to that thing. Or I could recognize that there's a rule for that. So this was A or not A is equal to 1. That was 12B again, just to list them in order here. And 10A tells us that if I have some input A, and I run that through an AND gate with 1, the output is dependent on A. So far we have A, and B times 1 is just B. And then now I just have A or B. But we're done. See if you can verify that using a truth table. Last one. This is just shouting distributive property at me. So we've seen that a few times now. I won't write out the rule again. It is rule 8A. So we have not A and B, or not A and C. We've seen that before. There's absolutely a rule for that. Rule 12A come into play a couple times, and it's down here. So we're going to use rule 12A that says A and not A. I've scribbled a little bit here. It is just A and not A are equal to 1. So we can simplify that as not A and B plus 1 times C. Well, we've looked at that a few times as well. 9A tells us that if I multiply anything, oh, sorry, that's this was A or not A. I said or. I'm using the wrong rule. 12A is A or not A, but what do we have? We have A and not A. Okay. Well, this is actually 12B. 12A is the one that we want, but it is A and not A run through an AND gate, and that's equal to 0. So we have 0 times C. All right. What do we need here now? 9A tells us A and 0 is equal to 0. If we already know one of the inputs is 0 and we're running them through an AND gate, the output is going to be a 0. So we're left with not A and B, or not A and B and 0, and then we could recognize that that's just not A and B through rule 9B. And we're done. Okay, I promise a quick look at De Morgan's theorem. How do we get from one to the other? So how do we get from not A and not B to not A or B on the right-hand side? Here's the general progression. We'll take that not A and not B, and we'll write the complement of each variable. So we have not A and not B. These aren't equivalent. These are just the steps to get from the original expression to its equivalent expression. And of course, a double negation cancels it out. So now we have not A and not B, but that follows directly. Those two are equivalent. And we're told to change all the AND operators to ORs. So I'll put in a plus as we change all the AND operators to ORs. So we first applied a not to each variable. We complemented each variable. Then we changed our AND to an OR. And if it had been an OR, we'd now change it to an AND. And now I'm going to negate the entire expression. Again, it's these two that are equivalent. Or we could have started with the OR and using the same steps returned to the AND. Try to work these out for yourself. I'm calling this magic, but it isn't really. It's simply applications of De Morgan's theorem. We'll see another application in this practice problem. Last one. Once again, I encourage you to pause the video and see if you can simplify this. It's not nearly as bad as it looks. And some of these we've seen a few times already. Recognize rule 12B, give it a go. All right, so 12B tells us that A or not A is equal to 1. So that simplifies it very quickly. We have not AB and not A or not B left. And sure, they're multiplied by 1, but anything multiplied by 1 is just 1. So we're going to start skipping steps a little bit. Now we can use De Morgan's theorem. We can start with either the first or the second and turn it into the other. These have a relationship. Turns out they're the same expression based on De Morgan. Right? If you look at 14b, we're told that not A or not B is equivalent to not A and B. So that allows us to turn the second set of brackets into an identical expression as that in the first set of brackets. And we know from 11a that A and A is just output A. So that's same here as well. Not A and B and not A and B is just not A and B. And while we could rewrite this, it's equivalent to A or not A or not B, of course, using De Morgan's. There's no reason to do that. It doesn't help us to simplify further, and we can leave it here.